Hey, welcome back. This is 11.5. We're looking at lines and planes in space, and we'll begin with doing lines. So creating the equation of a line, basically, we're going to be given some information. So a point on a line, we'll call that x1, y1, z1, and then some sort of direction. So basically a directional vector, A, B, C. And this directional vector is parallel to the line that we're trying to create. Okay. So the way this will work is to get the equation of the line, which we'll have two forms for it. We'll have the parametric form, and then we'll have the symmetric form. And where they get it, it's basically just the set of all points x, y, z, such that if you make a vector with the point on the line, the result will be parallel to this directional vector. Okay, so to say that kind of in math speak, we want the set of all points x, y, z, such that if you make a vector with that line, so how do I make a vector? You just subtract, right? So we have x minus x1, comma y minus y1, comma z minus z1. Okay, so that's just a generic vector, and then this has to be parallel. So parallel, that means a constant multiple of the directional vector. Okay, B, C. So usually we use the letter C when we were doing that previously. Basically we said what, like vector V is parallel to vector U if V is equal to a constant multiple of U, right? That's the same idea here. So this vector, again, that we've created, it's just a generic point such that it will be, when you make the vector with the given point on the line, it will be parallel to this other vector. Okay. So anyways, from here we can get the parametric equations and the symmetric equations just by equating components. Not given in the book would be the vector equation of a line. So usually in other books they'll give it as what is it? It's r of t equals what do we have? The slope, basically a, b, c. T plus this initial value x1, y1, z1. Okay, so this is not given, but in other books it is. It's the vector equation of a line. And you can see it looks just like the regular equation, y equals mx plus b. It's kind of the same thing. I think it's important, but the book doesn't really dwell on it. I think it's easier to remember this form. But anyways, from this vector equation, we can equate the components. So distributing this constant on the right-hand side, you would end up with x minus x1 equals at, which gives you x equals at plus x1. Then you get y minus y1 equals bt. So y equals bt plus y1, and then z minus z1 equals ct. So z equals ct plus z1. Okay, and so those equations there are your parametric equations for a line in space. parametric equations for a line in space. So this is in space. And then from the parametric equations, you get the symmetric equations. So by solving for t. So from the first equation, at equals x minus x1. You just divide both sides by a. So you get t equals x minus x1 all over a. And then from the second equation there, bt equals y minus y1. So solve for t, y minus y1 all over b. And then, of course, the third one, ct equals z minus z1. So t equals c minus c1 all over c. I don't really use the symmetric equations very much. Anyways, when they present the symmetric equations, you'll see on the right here, they set all three of these equal to each other. So you get x minus x1 all over a equals y minus y1 over b equals z minus z1 all over c. And these are the symmetric equations. Symmetric equations for a line in space. I don't really ever use the symmetric equations. I'm not even sure what in what universe they would be used, but they're used in the homework, so you need to have those for the homework. Okay, we'll probably use them in this section and then never use them again. Okay, one thing to note is that your answer may be different than your friend's answer, just solely because your point on the line might be different or something like that. Okay, so anyways, let's look at example 1 and see how this works. Example 1, find the parametric and symmetric equations. So they give you a point, 1, negative 2, 4, and then they give you your directional vector, 2, 4, negative 4. Okay, so again, it's the deal is it's a set of all vectors such that when you create a vector with a given point, it's a set of all points x, y, z such that when you create the vector, create a vector with a given point, it's parallel to the directional vector. So this thing will be a constant multiple of the directional vector. And I kind of always just start there. Actually, I'd be more likely to start with the vector equation of a line, but just to try to be somewhat consistent with the book, I kind of just do that. And then we have our vector equation, or parametric equations. So x is 2t plus 1, and y plus 2 equals 4t. So y equals 4t minus 2. And then z minus 4 equals negative 4t. And then z equals negative 4t plus 4. Those are our parametric equations. They also want the symmetric equations. So then you just solve each one of those for t. So solving the first one, 2t equals x minus 1. So t equals x minus 1 over 2. 4t equals y plus 2, so t equals y plus 2 over 4. And then finally, negative 4t equals c minus 4, so t equals some fancy footwork, 4 minus z all over 4. Get rid of that negative out of the denominator. And so our symmetric equations, x minus 1 over 2 equals y plus 2 over 4 equals 4 minus z over 4. So let's make sure that's right. Yeah, and I took the negative out of the denominator. I don't like the negatives in denominators. Okay. 2 plus 1, negative 2 plus 4t, 4 minus, okay, looks good. Okay, so there's other variations on this theme. So if you remember from pre-algebra, they would give you a point and a slope. That's basically this kind, and you have to find the equation of a line. That was basically this problem. Then they'll give you 2 points, and you have to find the, first put it into like point slope form and then solve for slope intercept form. That's kind of this next example that you see in the book. So example 2, they're going to give you 2 points and you have to find the equation of a line, right? So they give you -2, 1, 0, and then they give you 1, 3, 5. So very simply, to get, you already have a point, you just need the quote-unquote slope. So to get the slope, or in other words, the directional vector, you just make a vector out of these 2 points. So I'll let v equal the difference between these 2 vectors, or points. So 1 minus -2, and then we have 3 minus 1, and then we have 5 minus 0, which is just 5. So our directional vector, 3, 2, 5. Okay. Then again, you get your I guess your parametric equations and your symmetric equations. Once you get familiar enough, you could probably just go straight to the parametric equations. So it's always going to be x equals the directional vector times t plus whatever your initial point is, whether you want to use this first guy, the -2, 1, 0, or the 1, 3, 5 as your initial point. I'll just go with -2, 1, 0. So then -2, and then you can be a little careful with your signs. And then y equals 2t minus 1, and then z equals 5t plus 0. And then get your symmetric equations. So 3t equals x plus 2, so t is x plus 2 over 3. 2t equals y plus 1, so t equals y plus 1 over 2. And then, of course, t equals z over 5. So our symmetric equations, x plus 2 over 3 equals y plus 1 over 2 equals z over 5. Let's make sure that's right. They didn't want the symmetrics. Well, whatever, we got them. Looks like I screwed one of them up. So 2t plus 1 there. So see what happens if I don't go through the process. I end up screwing up a sign, but it happens. Anyways, that's the two basic type problems you'll see for equations of a line. Let's look at planes in space now. So to describe a plane in space, you basically need a point on the plane and then a vector that's normal, or in other words, perpendicular to the plane. So anyways, here we go. Planes in space. Okay. So this time, usually what you're given is a point in the plane. Okay. And then secondly, and we give this a name again, so x1, y1, z1. And then you're given a normal vector, vector normal to plane. And usually they give that the letters A, B, C. Okay. So this time the plane is a set of all points x, y, z, such that when you form a vector with this point in the plane, in other words, this vector x minus x1, comma y minus y1, comma z minus z1, it's a set of all points x, y, z, such that when you produce this vector and take the dot product with the normal vector, you get 0. Okay? Because any vector in the plane is going to be perpendicular to the normal vector. Let's see if we have a little picture for us over here. Yeah. So you're producing these PQ vectors, and those vectors will be perpendicular to this normal vector. So when you do the dot product of those vectors, you'll get 0, because the dot product of perpendicular vectors is 0. Okay, so from here, if you write it out, you get an equation. So it's a times x minus x1 plus b times y minus y1 plus c times z minus z1. And that is your equation of a plane in space. Okay, so this is your equation of a plane in space. Okay, so let's see if we can, if they give us one of these. Yeah, so that's a standard form for the equation of a plane in space. And then they have the general form. I think in the software, you could always just put in this standard form and it's happy. Let's find the equation of a plane given, well, let's do kind of, was there an example 2? Did I miss example 2 somewhere? No. Okay, well, is that example 2? No. Okay, so let's do example 3. So example 3, they're giving you 3 points in the plane, and they want you to figure out the equation of a plane. So we get 2, 1, 1, 1, 4, 1, negative 2, 0, 4. So the spiel is they're not giving you basically the normal vector. Okay, it's easy if they just give you a point and a normal vector. So just a sub-example here. If they give you a point and a normal vector, let's say 2, 1, 3, the equation of the plane is pretty simple. It's just 2 times x minus 2 plus 1 times y minus 1 plus 3 times z minus 1 equals 0. So that's real simple, right? This one is a little bit more work because they're not giving you that normal vector. So how do I get the normal vector? Well, you got to do a cross product based off the vectors that you can produce with these 3 points. So I'll just start creating some vectors from these points. I'll make the first vector the difference between the first and second points. So 1 minus 2, comma 4 minus 1, comma 1 minus 1. And that will be negative 1, 3, 0. And then let's get this other vector, the first and the third points. So negative 2 minus 2, 0 minus 1, and then 4 minus 1. I think I did that right. 2 minus 2, 0 minus 1, 4 minus 1. Let's make the other ones right. 1 minus 2, 4 minus 1, 1 minus 1. Okay. So I get negative 4, negative 1, and then 3. I need the cross products. I'm just going to cheat a little bit here and do my cross product. So the cross product will be 3 times 3 is 9, minus 0, and then negative 3 minus 0, and then the last one is 1 minus negative 12, so 1 plus 12. And then that will be 9, 3, 13 as my directional vector. Let's see if that's what they got. 9, 3, 13, yeah, good. So then you could just take any one of the points you want and create the equation. The book used the first point. I'll do that as well. So it'll be 9 times x minus 2 plus 3 times y minus 1 plus 13 times z minus 1 equals 0. And for the book, for the homework, I think you could usually just type that in as your answer. But if you are called upon to get the general form, you basically have to distribute 9x minus 18 plus 3y minus 3 plus 13z minus 13, and then combine like terms. So 13 and 3, right? 8, 9, 10, 11, 12, 13, 14, so 34. So you get 9x plus 3y plus 13z minus 34 equals 0. So this form, the book is going to call that standard. If they ask for it on the homework, I'm fine with standard form on a test or whatever. This one is called general. Right? let's see, angles between planes. To find the angles between planes, you can simply just find the angle between the two normal vectors, and that'll be equivalent to the angle between the planes because of properties of geometry. And so section 3, if you're called upon to do that, angle between two planes. All you have to do is figure out this dot product. So this is just from our like one of our first sections, the definition of a dot product, and you know, the magnitude of n1 times the magnitude of n2. And this will give us the angle between 0 and 90 degrees. That's why we got the absolute value there. Note the planes are, of course, perpendicular if the dot product is 0, and parallel if the normal vectors are multiples of each other. Anyways, let's take a look at finding the angle. I guess they don't give you one of those problems, but I stole one from the book. So determine if the planes are parallel. Determine if planes are parallel, perpendicular, or neither. And they give you two equations, x minus 3y plus 6z is 4, and the other guy, 5x plus y minus z is 4. So if you're just given the equation of a plane, it's pretty simple to get the normal vector. You just look at the coefficients on x, y, and z. So this first normal vector, maybe we should have some numbers on these. The first normal vector is 1, negative 3, 6. And then this normal vector is 5, 1, negative 1. Okay, so no big deal. Then, you know, you're looking at the cosine of the absolute value of the dot product, so that would be 5 minus 3 minus 6 all over the magnitudes. So 1 plus 9 plus 36 is 46, and 25 plus 2 basically is 27. So upstairs, negative 9 plus 5 is negative 4. Absolute value of negative 4 is 4 over the square root of the product of those two things. And then do cosine inverse on both sides, and you get theta is, you know, the cosine inverse of 4 all over the square root of 46 times 27, which of course is about 83 degrees from my calculator. So in this case, they're not parallel or perpendicular. Okay. All right. So there's that. I think I remember one question where they are finding like the line of intersection between the planes. So how does this work? So they give you two planes. 2x plus 3y minus 2z is 0. You basically do like a system of equations. You could set them equal to each other, or do like the addition method. I think the book does the addition method, so we'll do what the book does. It's 3y minus 2z is 0. So you want one of the variables to cancel out as you add column-wise. So I think if we just multiply the first equation by 2, that will do the job. That'll get rid of the z variable. So 2x minus 4y. 2x minus 4y plus 2z is 0. And then we got 2x plus 3y minus 2z is 0. So you get 4x minus y equals 0. And then you could solve for y. So y is equal to 4x. We want to kind of let x be a parameter or something like that. So you can let x equal t if you wish. Let's see what the book does. Do they let x equal t? Yeah, they do. Okay, so if x is equal to t, then automatically, so you want to produce a vector to describe this line. we kind of got the t, and then y will be 4t, and then we just need something for z. So you can plug 4t and t back into the original equation, so you get t minus 2 times 4t plus z equals 0. So you get t minus 8t plus z equals 0. So negative 7t plus z equals 0. And then you can add 7t to the other side. So then you would get your vector valued equation that you see in the book. I probably did it a little differently than what the book does, but it's the same idea as what they did. Okay. They note that if you do take the cross product of the normal vectors, you end up with a vector that's parallel to this intersection line, and that's what they're talking about right there at the end. Okay, drawing these things, so every once in a while it's nice to have a picture of what we're dealing with. So sketching planes. What you'll do is kind of let one variable equal 0 and kind of draw the other parts, and it's kind of like it's pretty simple, in other words. So I think maybe just doing an example is the quickest way to do it. And so I guess they're using this guy, 3x plus 2y plus 4z. I mean, you can do it a little quicker than what they're doing. So this is this an example? They're just not giving you an example or what? Okay, so anyways, I guess this is figure 11.49. And they talk about traces, which will be important once we get to the cortex. And what you're doing is kind of thinking about the projection or the intersection of the plane in a particular, the intersection of the plane in space with one of the xy plane, the yz plane, or the xz plane. So what they're saying is to let one variable equal 0 and then draw the resulting kind of line, I guess. But you could actually do it easier than that. You can let two variables equal 0 and then just plot the points on the x, y, and z axes. So on the x-axis, you can let y and z be 0. You get 3x equals 12, so x would equal 4. That basically means you have the coordinate 4, 0, 0. On the y-axis, if you let x and z equal 0, you get 2y equals 12. And so you have the resulting point 0, 6, 0. And then on the z-axis, if you let x and y be 0, you get 4z is 12, so z is 3, and then you have 0, 0, 3. Okay, and then you could go to your xyz plane and just plot those points and connect the dots, and you have a little picture. Okay, so 4, 2, 3, 4, 0, 0, 0, 1, 2, 3, 4, 5, 6, 0, and then 0, 1, 2, 3, and connect the dots. And that's basically a kind of a triangular section of the plane in space, okay, that you see over here in their picture. I need to do that. So the computer is so helpful, you know. Anyways, there's the picture. What they do is have you draw I think they're having you draw the kind of where the plane would intersect the xy plane, the yz plane, and the other plane. And what you get are equations of lines, and you just draw those lines in the 3 different planes. But this is way easier. Okay. All right. And then they have, you know, 2x plus. So what happens when you have one that's parallel to a coordinate plane like that? Maybe that's kind of the issue, because then you're not able to get that third point. Sure. So in this one, figure 11.5, you see there's no x, so all you have is kind of a trace, quote unquote trace in the yeah, so that one's a bit different. So I mean, you can always go and kind of go plane by plane, xy, xz, and then yz. And the xy plane, the y is 0. There is no y basically, but you'll have if you let z equal 0, you get 2x equals 1. So x will equal 1/2. So in the xy plane, you have the straight line right here at 1/2, which is what you see over here in the picture right here in this xy plane. In the xz plane, you just have the line z equals -2x plus 1. So it's going through the point 1, and then it's going down 2 over 1. So down 2 over 1, it's going to go like this. And that's what you see right here, this line here. And then the yz plane, you just have z equals 1, which will be this line here, which is what you see right here. Right? And then if you piece these together, hopefully you're able to draw the plane, but I don't know. I don't think it'll be that big of an issue later on, so I think we'll be okay. Okay, so after you stomach all that material, you start worrying about these kind of problems of distance between points, planes, and lines, and all of this just comes down to projection problems. So distances between points, planes, and lines. And so first we'll start with point and a plane. The distance between a point in space and a plane. And so you'll have a plane, an equation of a plane, and you'll be able to get the normal vector from that. And then you'll have some point floating around here in space. You can create a vector off of that point. So let's say the point is Q over here at x sub 0, y sub 0, z sub 0, and then we have a point in the plane here we'll call P, which we'll call x1, y1, z1, and the equation of the plane ax plus by plus c plus d equals 0. To figure out the distance from P from the plane to Q, you're going to take the projection of Q onto this normal vector. Okay, so that projection will tell you basically this perpendicular distance to the plane. Right, so you need to remember the projection formula. So the magnitude of the projection of this vector PQ onto the normal vector, which will end up just being this distance here that we're after. We had a formula for that back in the day. So if you remember the projection formula, it was so the projection normally PQ onto this would be the dot product of PQ and n all over the magnitude of n squared times n. This would be a scalar times that normal vector. So the magnitude of that thing is basically the scalar multiple of the unit vector n over magnitude of n. So you can rewrite it like this, and then you have this all over the magnitude of n. And then because this vector here is a unit normal vector, the length of the projection is just the absolute value of the scalar. Because if you remember, we had this theorem that said the magnitude of a scalar times a vector is just equal to the absolute value of the scalar times the magnitude of the vector. So if the magnitude of the vector is 1, then you could just pick off the scalar part, and that will be its magnitude. So the projection of PQ onto the n is just going to be the absolute value of PQ dotted with n all over the magnitude of n. Okay, so let's try one of these examples and see if we nailed it or not. See if I need to go back to the drawing board. So example 5, they're giving you a point Q in space 1, 5, -4. And then they give you an equation of a plane, 3x minus y plus 2z is 6. So I need to find this PQ. So to get PQ, you just randomly pick a point in the plane. And what the book did is to use a real easy point by letting y and z equal 0. So if y equals 0, z equals 0, you have 3x equals 6, so x equals 2, so you get the point 2, 0, 0. And then from there, that'll be your point P, and you could get that PQ vector. So PQ will equal 1 minus 2 is -1, 5 minus 0 is 5, and -4 minus 0, -4. So you get your PQ, the normal vector, of course, you could just read the coefficients off of the equation of a plane, so 3, -1, 2. And then we just use our equation up there. So the distance will be the absolute value of the dot product, so -3 minus 5 minus 8 all over the magnitude of the normal vector. 9 plus 1 plus 4 is absolute value 14. So this looks like we get 16 all over square root 14 as our yeah, that's what they got. They try to generalize it and give you a formula. I don't think that formula is very helpful, so I never use it. But there it is in the book. It's like, good luck memorizing that, you know. Anyways, we can kind of go from this kind of question to now finding the distance between two parallel planes. So I guess part 2 here, distance between two parallel planes. And it's the same formula. It's just if you have two parallel planes, all you have to do is get a point in one of the planes, and then just pretend you're getting the distance from one of the planes to the point, and it becomes a point plane problem, and you just can use the same formula. Okay, so let me show you what I mean. So this example 6, we have 3x minus y plus 2z. Minus 6 is 0, and then the other one, 6x minus 2y plus 4z plus 4 equals 0. So you just use this to get a point. So let x equals 0, y equals 0, and so you get 4z plus 4 is 0, and 4z will be -4. So z is -1. So you get the point 0, 0, -1. And then get a point from this plane. So let this point be your Q, and then get a point P from this other guy. So we could let's go with letting y and z be 0. So y equals 0, z equals 0. So you get 3x minus 6 is 0, and then 3x equals 6, and then x is 2. So you get the point P, this time is 2, 0, 0. Then form your vector for PQ. Okay, so 0 minus 2, 0 minus 0, -1 minus 0. And then you have your normal vector from the plane that you got P from. So that's going to be 3, -1, 2. And then you use the formula from before to get your distance. Okay, so it's the dot product, absolute value dot product, -6 plus 0 minus 2 all over the magnitude of the normal vector. So that's 9. It's 14 again. And then you get 8 all over square root 14, okay, which is what they got using the formula. But like I said, good luck remembering that formula. I always just generate it from the projection formula, because you got to pretty much hopefully have that projection formula memorized to some extent. And then you just work with the projection formula onto this. Yeah. Okay. So it's just a projection of this vector formed from a point in the plane and this point in space projected onto the normal vector. Okay, the third type of problem that you're going to see in the book is the distance between a point and a line in space. And this one is a bit different. So 3 point and line. So you're going to have basically a vector for a line, and you can get a point from that, a point on the line. And then there's going to be a point out here in space. Let's call the point on the line P, the point in space Q. To get the distance from the line to the point, you basically need this distance right here, which I can call D. If you make a vector between okay, so hold on. Let's call this theta. Let's call this u. All right. So I have formulas that from trig that will relate some of these unknowns. So the sine of theta is equal to opposite over hypotenuse. So the d is what I want. The length of the hypotenuse is the magnitude of PQ. So I could say d is equal to the magnitude of PQ sine theta. This, you may or may not remember, is similar to kind of the dot product formula, but with cross products, right? So remember the cross product of PQ and U would equal the magnitude of PQ times the magnitude of U times sine theta. And then you can solve for magnitude PQ sine theta by dividing both sides by magnitude of U, and you get magnitude PQ, which is the distance, times sine theta, which is that distance we're after, is equal to the magnitude of the cross product of PQ and U divided by the magnitude of U. Okay, okay. And that then is the formula du jour that we kind of need to complete these problems. So let's take a look at example 7 and see how this works. Okay, so example 7. We have a point, so Q, 3, -1, 4. Then we have the parametric form for the equation of a line in space. It's 1 plus 4t. And so the vector u is basically the directional vector of that line. So it's easy, just pick off the coefficients of the t's, 3, -2, 4. And then for PQ, you're going to have to get a point on the line, right? So you could let t equal 0 and get a point P on the line. So that would be -2, 0, 1 when t is 0, and that's a point. So the vector PQ, taking the differences of those points, would be -2, -3, so that should be a positive 3. -2, -3, and then 0 minus -1, and then 1 minus 4, so -3. So PQ is -5, 1, -3. Did I screw that up? Oh, I did QP instead of PQ. It's you know, it's not going to matter. I don't think it'll matter. So let's try it anyways and just see if we get the right answer. I don't see why it would make a difference. PQ and QP will have the same length, right? So anyways, let's try to get the this cross product thingamajig. So PQ cross with U, and we're going to need the magnitude of that eventually, but let's just get PQ cross with Q. So it's going to be -5, 1, -3, and then -2, 0, 1. So I'm doing a cross product here. I don't need all that jazz. IJK. So I get 1 -0 and then -5 -6, and then finally 0 minus -2. So 0 plus 2 is 1, 11, and then 2. Okay. Whoops, I did not use the right points. Ugh, this one's falling apart big time. Sorry, guys. I didn't use the vectors. So 5, it should be 3, -2, 4. Sorry. Okay, so, all right, so, and I still have to give you the video quiz. I haven't forgotten about that. So it's going to be 4 minus 6. Let's see what else. -20 minus -9, so plus 9. And then finally 10 minus 3. And we're going to get -2, -11, and then 7. And then we need the magnitude of that. So the magnitude of this cross product is going to be the square root of 4 plus 121 plus 49. 149, 4, 14, 4, 5, 6, 7, 174. So the distance is going to be 174 all over the magnitude of U. So that goes U. So that'd be 9 plus 4 plus 16. So that'd be 29. So 29 should be our final answer. We get a square root in there, I forgot. Yeah, so square root 174 over square root 29. I think that's really it for that. You know, on a test, I probably wouldn't ask you for the distance between a point and a line. It would be mainly plane and plane or point and plane. Let's see what they got in homework and maybe do one of these for the video quiz problem. Some graphing. So the graph of z equals 2. Basically, so you just go up 1, 2, and then basically you have a plane going through that point. So if you want to make it look dandy, you can kind of cheat a little here. And make it look like that, make it look like the line's going through the plane or something. And this is the point 2 on the z-axis. So they're doing some planes. Find the distance between the point and the plane. Find the distance between the point and the line. Let's try number 19 for the video quiz. Let me mark in my notes. So this is the video quiz for 11.7. Oh no, 11.5. So number 19. Okie dokie. So find the distance, because I kind of butchered that example. They're giving us 2, -2, 3. So that would be like our Q point. And then our equation of the line is t minus 3, c is 2t plus 2. So let's get a point P on this line. Let t equal 0, so you get 0, negative 3, 2. I need my normal vector, or sorry, my directional vector, which I'll call u. That's just going to be 2, 1, 2, and then get PQ. Okay, so that would be, this time do it right, Dave. So 2 minus 0, negative 2 minus 3 is negative 5. It doesn't make a difference, but 3 minus 2 is 1. Sometimes I don't like to mess around. So PQU, I need that cross product. And so I got 2, negative 5, 1, 2, 1, 2, IJK. So we're getting negative 10 minus 1, negative 4 minus 2, and then 2 minus negative 10, so plus 10. So this will be negative 11, negative 2, 12. And then I need its magnitude for my final answer. So it's the magnitude of PQ cross U all over the magnitude of U. So I got the square root of 121 plus 4 plus 144 all over the magnitude of U, which would be 4 plus 1 plus 4. Being more careful this time. In the numerator, I got 121 plus 4 plus 144. Not messing around, using a calculator. 269 all over the square root of 9, which of course is 3. What do they want? 3 decimals. Let's make sure it's right. Square root 269 divided by 3 is not the appropriate answer. And this is between the point and the line. And the answer with 3 decimals. Gee willikers. Oh, I see a mistake already. So negative 2, it's back here in PQ. I apologize. So the first one, 2 minus 0 is fine. Negative 2 minus negative 3. Let's make sure that's right? Negative 2 minus negative 3. And the last one was 3 minus 2. So that would be 2. Negative 2 plus 3 is uno. Okay, so that's going to screw up this guy. 1. So that's going to screw up all this junk. Sorry, folks. And so 2 minus 1, 2 minus 1, and then cover up the middle guy. 4, it's negative 4 minus 2, and then the last guy, 2 minus 2, it's just 0. So that's going to be 1, negative 2, 0, so that's going to be 1 plus 4. So square root 5 over square root 9. So square root 5 divided by 3 gives me that's right, 0.745. Okay, so that'll do it for this video. Thank you for watching, and we'll see you next time. So that was the video quiz. This last question, number 19, was the video quiz.